The last session, it's my pleasure to thank the organizers. Although it was done last night by Shimon, it's worth doing again. I'd like to thank the physicists, Eliezer, Colby, Marek, and Adam, as well as the staff, Mr. Haik in Jerusalem, Ms. Cohen here in Tel Aviv, for a very well-organized meeting with extremely well-chosen topics and extremely well-chosen speakers. Also like to thank Eliezer and Shimon for providing the occasion. And I'd like to see all of you in 2017. Our speaker is David Gross, who gave me the title of Perspectives.
I think so. Well, it is a pleasure to end this conference, not because it's been a wonderful conference, as you all know, but I'm sure you're all tired, as I am. There have been so many wonderful and exciting and contentful talks that I thought it would be a good idea on this happy birthday to celebrate of course, we're all celebrating, to end with some light entertainment. So you can wake up and be assured that there will be very little content to my talk. I have no new physics to report. I must say, you know, sitting in this conference and hearing all these wonderful talks, I feel a bit envious. One of the prices of a Nobel Prize, and you know, you might think it's just silly, it's really hard to do physics. Not because you felt that, you know, how could you ever surpass, et cetera, that kind of thing, but just because the demands on you are so extraordinary. So this conference has really been good because there have been so many interesting ideas and wonderful physics that I think it's going to stimulate me to start saying no. I couldn't say no to Eliezer and Shimon, and I'm delighted that I didn't, and I've really enjoyed myself, as I think we all have. It's been a warm and stimulating environment, as it always is when we visit Israel, and it's been great. So, but I will say a few words and try to entertain you a bit, and maybe a bit of preaching about string theory and where do we stand. String theory, as we all know, is a very old topic. Almost 40 years? It's hard to believe. Yeah. And where do we stand? One way of judging where we stand is to look at the popular perception of string theory. And I sort of collect cartoons. So I have a cartoon that I often used to show in popular lectures on string theory, which appeared in the New Yorker, I think probably 20 years ago now, where you have this couple of intellectuals in the village. That's how I explain it to Europeans. I explained that they're obviously intellectuals because he's wearing glasses and he has no hair, and you know that's what the New Yorker. And she's saying to him, "It's all string theory to me." And you know that was sort of the perception of string theory for a long time. Something profound, even more profound than Greek. And I like that, sort of. Well, here's some recent cartoons. Here we have some recognizable characters. This one is soon to be indicted. And this one is saying, Carl, I got a big funding request for string theory. Is string theory consistent with intelligent design? And Carl says, yes, string theory is consistent with everything. Or anything, actually. It all depends on which type of universe we are. If you fund it, it just confirms that it is consistent with intelligent design. Yeah, that's yours. And George says, I like it. This is really easy to fund. Well, that's a bit disturbing, but at least the conclusion. Honey, it's a swing here. Yeah. That's a bit disturbing, but at least the conclusion is comforting. The next one is a little worse. And I think, I forget who gave me this one. I don't know where it's from. But this guy's walking by the bar at Harvey's place. Tonight, 5 to 8, is string theory bullshit. Now, what does this mean? I mean, have Smolin and Voigt have such an impact? Maybe. But not all public depictions of string theory are that bad. Here's another one that was sent to me, and it shows that some of the public, at least advertisers, think string theory is really sexy. This is an advertisement for underwear, and it says, string theory, when physics gets physical. So our problem, in a sense, is that string theory hasn't gotten that physical yet. I mean, here we are 40 years later, more than 2 decades after the string revolution, where we hoped that physics, real physics, was around the corner. 10 years since the last big revolution, which we're still reaping the benefits from. It was kind of interesting, I thought, to note that at this conference, only about less than half the talks were actually on string theory, even though this was devoted to the achievements and perspectives of string theory. And, well, that might have something to do with the average age of the speakers, but it also, to some extent, is symptomatic of the problems we face in string theory, which I'll come to. But I do want to stress, of course, that I am still a true believer in the sexiness of string theory and its ultimate potential. It's clearly, and I think most people in this room believe that, on the right road. But it also has problems. But the achievements are significant, and we should not shy away from reminding ourselves, as I do when I try to counter these impressions in the general public, how much string theory has achieved. It is something new, different, an extension of physics. It might be, in fact, a revolutionary extension of physics, completing the others. It certainly isn't so far, less than I thought, in fact, originally. But it might be, and it's hard, and we haven't really had any other alternatives for the beginnings of a conceptual extension of relativistic quantum field theory, our existing framework of fundamental physics. It is a consistent and finite quantum theory of gravity, at least for weak fields, perturbatively and semi-classically, and that's a lasting achievement. I think it has, for almost everyone, dispelled the notion that there might be an inconsistency between general relativity and quantum mechanics. And most impressively, at least one of the major paradoxes of semi-classical quantization of gravity, the properties of black holes, and the unitary time evolution of systems containing black holes has been resolved. But of course, the most important prospect that string theory promised us originally was a rich structure that could describe the real world and seemed to have within it a remarkable degree of uniqueness, which only increased over the years in one sense, and no apparently arbitrary parameters that seem to have all the components we find so far in the real world. And it's understandable why 2 decades ago we had expectations that with all of that in hand, real physics wouldn't be far behind. But we clearly are less optimistic today. And these achievements are all real and remain and are the reason we continue in the absence of any direct experimental evidence or in the absence of any impressive calculations of real physical phenomena that and we do so partly, well, because of the incredible richness of the theory, the lack of any competitor for a logical extension of the conceptual framework, this enormous success, conceptual success of reconciling quantum gravity, quantum mechanics, and general relativity, and for the fact that it's also true that we've discovered, or both from theoretical investigations and experiment, no new phenomena or qualities of the real world that we don't think fit in to string theory, with perhaps the exception of the cosmological constant, which I'll come to. But aside from the great successes, and this slide hasn't changed much over the last decade, we also have failures. And I think the main failure is that we still don't know what we're talking about in a sense. And of course, I want to, I made a statement that we don't know what we're talking about in string theory, and that immediately became a headline in the New Scientist. Noted string theorist says string theorists don't know what they're talking about. So, of course, we know what we're talking about. We just had 4 days of wonderful talking about string theory with great precision and beautiful calculation, some incredible calculation. We know what string theory is, but in some sense, we all know that we don't know what string theory is. So, if you really ask yourself or ask each other, what is string theory? You might start by describing how to construct particular calculations of particular observables in string theory. But what string theory is in the sense of what, Schrödinger equation for atoms is, or what QCD is, we don't know what string theory is. We don't really have a way of formulating string theory. In fact, we might not even have one theory. We have a vast array of different formulations which allow us to calculate the properties of string theory in different domains, in different regions of the theory where we can do consistent semi-classical expansions. And as you all know, the famous Polchinski's picture of the space of string theories, these little corners which we can control, are, we think, just a very small domain of string theory, most of which we can't control, and worst of all, we have no idea what it is that these are approximations of. This is a rather unprecedented situation in my mind, and it is one of the great lessons of the revolution that occurred a decade ago, to realize that the same theory in different domains can be described by things apparently as different as the 5 original string theories describing perturbatively extended objects moving in some background space-time, or M theory, which we don't understand much beyond 11-dimensional supergravity. But those are equivalent to ordinary gauge theories in 4 dimensions, or in one case, which I still regard as the most remarkable duality of all, to supersymmetric quantum mechanics with no space at all. The fact that, in that sense, theories which have no gravity and much fewer spatial dimensions, or in this case, no space at all, can also be equivalent to theories with gravity. Gravity is emergent, as is most or some of space. I still find that astonishing, and I don't think we have come close to truly understanding the implications of that, but we certainly have no idea of what it would mean to have a formulation of some kind of theory, well-defined theory in the traditional sense, to which all of this would be an approximation in some well-defined limit. We don't even know whether it makes sense whether such a traditional definition of a theory will happen or exists. And the other thing that I find kind of remarkable is that, I really thought string theory was different than field theory. It was something really new, which happened when one considered the quantum mechanics of extended objects. But now in these dual formulations, we see that string theory is no different. It appears, or can be described in our best description in certain backgrounds of string theory non-perturbatively is ordinary field theory. Is string theory really different than field theory? So, when I give popular lectures about string theory and some wise guy gets up and tells me that, well, they just read this book about loop gravity and that seems like a viable alternative. What will it take to kill string theory? I say you can't kill string theory. You can't kill string theory because the standard model is string theory. We believe somehow that all gauge theories in 4 dimensions are continuously deformable. We heard explained the power of that duality and argued as well that there's very likely that we can get the QCD, maybe even the electroweak model, maybe even any field theory. But certainly Yang-Mills theory in 4 dimensions seems to be continuously connected to a asymptotic expansion about some point in moduli space of the thing we're calling string theory. So is there truly anything different between string theory and field theory? Well, that's good from one point of view because you can't kill string theory. So it's not as if somebody's going to come along and say string theory is wrong, because you'd be saying that field theory is wrong, the standard model is wrong. And even the Swedes have agreed that standard model is correct by now. So, but on the other hand, it's disappointing, because string theory, or whatever it is that we need to achieve the goals we talked about, we think has got to be, certainly if it's going to complete the trio of revolutions associated with the three fundamental dimensional parameters of nature, be in some way truly different than relativistic quantum field theory. So what is missing? You know, I, of course, have no idea. But one important question in trying to answer this question, what is string theory? How do you define it? Is that maybe it's not a theory at all. Maybe it's a framework. Quantum field theory is a framework, not a theory. You could imagine relativistic quantum field theory. If you principle, one could imagine the space of all Hamiltonians, the Wilsonian playground. And quantum field theory, in that sense, is not a theory. It should be called quantum field framework. It's a set of theories. In order to specify a particular quantum field theory, you have to choose a dynamics. But that we understand and are perfectly comfortable with. It's a limited kind of theory. It was never a candidate for a theory of everything. You had to choose the couplings, the interactions. You could dial parameters, and you could see in how you defined a particular quantum field theory, how you could alter it and move from one theory to another. Whereas in string theory, there's nothing you can modify. You don't have any freedom to change the theory in the traditional sense of modifying parameters or changing the interactions or adding new degrees of freedom. The only freedom you have is to choose, is to consider different backgrounds or different approximations, different starting points for constructing the Hilbert space, the quantum mechanics in a semi-classical fashion. Now, this is something that, you know, when I listen to Tom Banks, it resonates to I have a sort of a half resonance with Tom on many of these issues. And he certainly has spent a lot of time thinking about this deeply. And I don't know what the answer is. But clearly something, the fact that after 40 years we can't formulate what it is we're talking about is a suggestion to me that something is missing, and not clearly missing in the traditional sense. But, you know, that's the usual case. I don't know what is missing. But it seems to me that it might not be unrelated to the main problem we face in trying to make real predictions and calculations from string theory, this enormous richness of theories or solutions of a given theory, the enormous number of vacua, and that missing something, I would suspect, has something to do with the fact that for the first time we are faced with kinds of questions that we never had to face before, that people working in quantum gravity and cosmology have thought about. They clearly didn't have the tools either, and that the nature of the questions is changing. We are required now not to construct a vacuum. We're not interested in a static, time-independent solution of whatever it is, whatever theory we're talking about, but rather a time-dependent space-time. The object of consideration is the space-time itself. And not just the end, which we heard some lots of interesting discussion about from Steve and from Tom, but rather the whole space-time, including the beginning, which everyone avoids because although string theorists at some point armed with progress in string theory started to tackle the question of the beginning of the universe, and after encountering roughly the same problems that quantum people working in quantum gravity semi-classically or classically encountered, dropped it like a hot potato. But the beginning is just as important as the end. And we actually really, in my opinion, have no idea what the rules are. So to paraphrase Bill Maher, a profound political thinker in the United States, what are the new rules? Personally, I really think this has to do with our understanding of space and time. And we all know by now that space, in the traditional sense, degrees of freedom localized at spatial points. Space itself and the dynamics of space, gravity, is not fundamental. And we have the examples I discussed previously, which are the most well-defined descriptions of string theory. Matrix theory originally, and ADS-CFT, which has proved so powerful, in which all or some of space emerges, and gravity, as the dynamics of the metric of that space emerges as well. We have really no examples of emergent space-time, which should happen as well. So, I suspect the answer lies there and in the issue of what are the rules for determining a space-time manifold as the answer to the question, to a question we don't know how to pose in a theory we don't know how to formulate. Okay, well, that's the sum of the problems. However, there's no question in my mind that string theory, or what it will evolve, has these hopes still remain, at least in my opinion. A unified theory of all the forces, new concepts of space and time, and resolving some of these problems. However, meanwhile, and a good part of the most fascinating talks in this conference were the incredible new insights we can get into gauge theory. There was even a discussion of insights we get into mathematics, new phenomenological scenarios, and we've heard quite a few of those here, new. And what I like especially is the impact of string theory back on its original motivation on the strong interactions, the attempt to derive and control analytically QCD in the infrared to derive the QCD string. And here there have been remarkable developments based on ADS-CFT duality in the last few years, and this is a great contribution, I think, of string theory to physics that we know is there, and will and has produced, in addition to the traditional goal of understanding hadrons and, say, in the zero-width large N approximation as strings, new insights into things like the QCD strongly interacting plasma, which were surprises. They were not just trying to reproduce quantitatively qualitative features that we knew and understood about hadrons, but to some extent discovered theoretically new features of the quark-gluon plasma that seem to be there remarkably.
In this picture we have that longitudinal but it's not really.
Yeah, well, these are very heavy quarks, and this is a static potential, so it looks pretty. You can see a string. So this is, of course, based on this incredible duality between gauge theories and string theories that has been exploited so much in the last decade. And this, still remains after 10 years the most powerful tool we have in both directions. But, let's talk about the dualities. The hope of understanding QCD using string theory, the original motivation for string theory, was to use the string theory, once you found it, that corresponds to the large N limit of QCD, to learn about gauge theories. And as I said, remarkable progress has been made, but it's a little disappointing, even with this incredible progress. So we heard a discussion by Igor, which showed us this unbelievable progress that has been made in calculating properties of QCD based on this attempt to exploit the duality between gauge theory and string theory. But you'll notice that the most powerful of the results that he quoted, the calculation of the anomalous dimensions of these twist-2 operators exactly, was a gauge theory calculation. Now, I would have thought that once you had this explicit duality between string theory and gauge theory, the idea was, well, the string theory is a classical string, and you just solve it, and you have the spectrum, and you learn about an impossible task in gauge theory of summing all planar diagrams. And yet, for some reason, what's actually happened is that the gauge theory techniques have proved more powerful. They're based on integrability, whose strongest argument perhaps comes from string theory, but the real calculations are based on gauge theory methods, and they still are more powerful. This is a common theme. Our knowledge of field theory is so much more powerful than our ability to do even classical string theory. It's a bit disappointing. But this is going to be, I think, continue to be useful for a long time. Mostly, however, it's supergravity applied to gauge theory, as is most of our control over interesting situations in string theory. The other direction is rather weak, actually. I mean, we can say a lot about gauge theories. We have enormous power over field theories. And that should have all sorts of implications for string theory. But very little of that has been exploited, as far as I can tell. For example, we have total control over n equals 4 Yang-Mills theory for weak coupling. That must have very interesting implications for n equals infinity, and even more so for finite n, for highly curved ADS space, and maybe even at strong coupling. And there's very little that has been learned. I think mainly we don't know how to ask the right questions about the theory, about the quantum gravity or string theory. We have the answers. We don't know what the questions are. So the real problem there is think of a question because you have the answers. And in a regime that is so far away from where you understand quantum gravity or string theory, and strengthen this duality. So now let me come to a topic that has been much discussed here, the landscape. So we've had a whole variety of discussions about the landscape, which is sort of a background in which much physics is being done nowadays. And you all know what the landscape is. There are a multitude of possible universes, metastable states, and they have almost a continuum of cosmological constant in particular, and there's no particular reason why we live in any one of them, we invoke the entropic principle to strongly constrain the universe we find ourselves in. Well, this point of view and this approach to string theory and to physics is, unfortunately, perfectly logical. It requires two facts, well, two phenomena, of course, that there exist large numbers of universes within which most of the fundamental parameters, but certainly the cosmological constant, varies. And the parameters that govern, certainly the cosmological constant, the universe, are rare. Now, the argument that was always the premise behind uses of the entropic principle for the last 120 years or so. But recently, the proponents of the landscape have argued that in string theory there is now evidence for that. Namely, the many flux string vacua, or metastable states, that people argue should exist, whose cosmological constant is a sum, it would appear, of, at least semi-classically, of a large number of terms with varying signs. There are so many possibilities that this almost gives a continuum of values from minus the Planck mass to plus the Planck mass. Then the second component is that there exists some kind of dynamical mechanism that populates this ensemble of universes, and as has been stressed by the inventors of inflation from almost the beginning of inflation, internal inflation is a perfect mechanism for doing this. This mechanism has been around forever, and we all used to go, string theorists used to go to talks by Andre Linde for years with pictures of the landscape, and no one took it seriously until recently, and mostly until the cosmological constant was actually measured. Well, this is all true. You need two things, and there certainly is. There are two reasonable ideas which are related to theories we love and cosmology that we like and seems to be confirmed by data. But does the landscape really exist? Well, these vacua of string theory, as the proponents will admit, are all metastable. Most of them are totally uncontrollable, and no one discusses 10 to the 500 of them. They usually focus, as we've heard, on simple examples where you can, in fact, discuss them with semi-classically with extraordinary beauty and precision and get lots of interesting models. I mean, it's wonderful. But are they really controllable? They're all metastable, so as the answer is supposed to be a space-time manifold with a beginning and an end. All of these have nasty beginnings, and most of them have nasty ends. What does that mean? A lot of we've heard some this conference very interesting discussion from Tom, who worries about this a lot. And if you believe him, he'll tell you that 99.99, I don't know how far I have to go out, of these things don't exist at all. What he means by that, now I'm not sure I believe him, and then he goes on to, from there to, nested diamonds, and I lose him, but as an example of a, it could be, I feel very uncomfortable about just taking at face value the argument that because you could exhibit using very crude semi-classical arguments metastable states, whose lifetime is long compared to the lifetime of the universe, without addressing the beginning, most importantly, in my opinion, and the end, that you really can argue that that's consistent. I had an interesting discussion with Steve at some point. He was saying, well, you know, David, it might be true, there's real shit, but the correspondence principle should work. If you're in a regime where you can trust semi-classical arguments, and anything you calculate sort of tells you you should trust them. But I'm not sure that's true. And I reminded him of the trouble that Bohr and Kramers and Slater got into just before quantum mechanics was born, when based on their firm belief in the correspondence principle and the ability to trust semi-classical arguments and so on, so they were led down a path which they were willing to do things even worse than the entropic principle, namely give up energy conservation, except on the average. The difference there was when they suggested that energy was only conserved on the average, experimenters went out, measured the Compton effect with a millisecond time resolution, and were able to show that energy was conserved on very short time scales. And Bohr immediately said, okay, I'm wrong, dropped it. Kramers didn't. And it seems that's why he missed discovering quantum mechanics. The other thing I really find shaky, and again, not that I can have a real argument what goes wrong with is the mechanism of eternal inflation, because of the fact that one is discussed. Well, we all know the reasons why. I won't elaborate. But the real reason that people take these ideas seriously, no question about it in my mind, or in Lenny's, as he said from the beginning, is the cosmological constant. I mean, we have these fluctuations in the vacuum. We know, we see them, we observe them, we measure them, and no matter how we think about it, they're bound to give rise to an enormous energy. Supersymmetry, we originally helped, but it's broken. That doesn't help very much. And that's always been a problem, but there's nothing like measuring something to make it a real problem. And this, I think, is clearly what has motivated the pessimism that we could come up with a unique vacuum or a unique universe. Because how would we ever calculate such small numbers down by, we all believe in supersymmetry, so say down by 64 orders of magnitude. Well, it's not the smallness of this number I don't think should bother you. That's not a problem. We're used to small numbers. We're used to large numbers. Dirac, who was the first to have notice a large number problem, as far as I know, said that, well, the proton-Planck mass ratio is such a small number that one's going to have some revolutionary explanation of the small number. Now, Dirac could have invoked the entropic arguments. He didn't. Dirac had, well, Dirac could have invoked entropic arguments. I mean, it's easy to come up with an entropic argument. If this number was of order 1, molecules would be black holes. So this number has to be very small for planets, life to exist. He didn't invoke entropic arguments. Instead, he made another revolutionary hypothesis that this ratio is related to the size of the universe in atomic units. The advantage of that hypothesis was a prediction. The size of the universe varies, therefore, Newton's constant and alpha, I mean, he had other large, would vary, and this prediction has been tested and measured over the years, and we're pretty sure that, or we see, every once in a while, people start seeing variation in alpha, but it doesn't appear to be there, certainly at the rate of the Hubble expansion. But we, particle physicists, standard model, have solved this problem. We can calculate this number of 10 to the minus 19. In fact, we do so in QCD. The mass of the proton compared to the Planck mass or the unification scale or wherever it is that the couplings become weak, like in string theory or grand unified theories, generates a dynamical scale by dimensional transmutation where the coupling becomes strong, which is easily, in fact, pretty well, is 10 to the minus 19. What is observed? The proton mass is calculable. And there's a trick here, of course. It's taking a logarithm, but the logarithm here is real. It's the logarithmic running of couplings in four-dimensional gauge theories. So, in fact, that incredibly small number is a triumph of QCD. And we no longer regard it as a big mystery. Maybe we can't calculate it with a precision better than a factor of 2 or 10 because we don't have total control of the unification scale. But we've accounted for most of the 10 to the minus 19. And we've explained other equally, or close to similarly small numbers that we think we can come up with explanations. The hierarchy, the very smallness of the electroweak scale compared to the gut or the unified scale. Again, we can understand if we now invoke a new mechanism called supersymmetry, one of the main arguments for supersymmetry, plus the same logarithmic variations. And a third example is, of course, the neutrino masses, which are exceedingly weak, small. Less than that. And there, too, with a new mechanism that was invented and is very natural in our ideas of unification, beyond the standard model physics, certainly string theory, we can explain that very small scale as well. So the problem is not the cosmological constant. The cosmological constant actually isn't so small. In the correct units, it's a mass to the fourth. So if we take the fourth root to compare it with these other problems, I mean, the mass density, energy density of the proton compared to the Planck energy density is 10 to the minus 76. So, using our ideas of supersymmetry, we have a problem that we have solved 3 times, at least conceptually, before.
David, when you start calculating cosmological constant, adding up the numbers,
The problem.
is lambda, not lambda to the 1/4.
I'm comparing the nature of the problem. I can calculate the fourth root of lambda just as well as.
Calculate the 25th root of it.
Yeah. Anyway, the problem is not that it's so small. I don't see it. That's the problem. The problem is that we don't understand any I'll give you, Lenny, just to answer your question. Tom gave a very interesting idea, not of calculating lambda, but of relating it to a mass. Okay? And he was relating it to a mass of a few tenths or something of electron volts. But he wasn't relating the fourth power of that mass, but mass itself. So I don't regard this as a problem, the smallness, the incredible smallness. The problem is we don't understand a mechanism. And there I totally agree. If we simply add up things, there's no question then it's totally absurd to be able to determine it, unless you have 10 to the 500 things you add up and choose one out of the 10 to the 500, which is your mechanism. That indeed is the only mechanism that I know of, except for variants of the Abbott mechanism, which someone might find one that works, and we heard about that. The anthropic arguments are the most naturally, appealing in a sense. They give but you have to swallow a lot. So I'm going to end with my preaching. About the dangers of this entropic principle. If you invoke it for that reason, you have to go along with a lot of other things. It is really impossible to falsify. It's not like Dirac. You could easily falsify Dirac's suggestion about the solution of his hard problem, which is sort of a very small number. And as we all know, these arguments, entropic arguments, are often tautological. My real objection is just the feeling that this is ahistorical. It just goes against the grain of the progress of physics, which is absolutely remarkable, and we are, of course, very proud of it. To imagine today, 100 years ago, that the entire normal observable world, all of atomic physics, all of condensed matter physics, all of chemistry, all of life, we believe, is explainable by ordinary quantum mechanics, the Coulomb interaction, which, if you think about it, up to a scale given mass of nuclei is determined by one number, one structure constant, is amazing. And much of that wonderful world, all of which we can calculate exactly in principle, has weird properties necessary for life. But the real problem I have with the entropic principle is that it's an easy way out, and that it's just too easy to say when you encounter a problem, well, there's an entropic explanation. So about a month or two ago at a KITP workshop on biology, the entropic principle was invoked in a very interesting talk by Dr. Eugene Koonin, not related to Steve, from the NIH, called The Cosmological Model of Eternal Inflation and the Transition from Chance to Biological Evolution in the History of Life. And many of the astrophysicists present at the KITP and the high-energy physicists came to his talk because of the title. So, a good part of this workshop was on trying to understand how evolution works at the molecular level. And part of it's the origin of life. It's a hard problem. The impossibility of the origin of life is the main argument, as you know, of creationists and people in intelligent design. So at least from a political point of view, it's very important for biologists to show that life is possible, could have evolved naturally. But it's very difficult. And most of the pathways they explore run into the problem that they consist of so many unlikely paths, especially at the beginning when you're trying to create the life from just a soup of amino acids, then it seems extraordinarily improbable. So this guy was inspired by reading and long discussions with Alex Valenkin, who has written, as you know, a lovely book called The Many Worlds in One, where he discusses eternal inflation, as did Lenny. And in fact, he has pictures. This biologist showed these pictures, which look very much like Lenny's pictures. And the main problem he was faced was that in his attempts to create, using biochemistry that that he knows and tries to measure in the laboratory, the so-called RNA world, which is thought to be the pathway to life, it just seems absolutely, totally improbable. The rates you calculate, the number of steps, so on and so on. So he was advocating, therefore, that since the cosmologists and the physicists, according to him, have come to the conclusion that there are an infinite number of worlds, all equally likely, and the world we live in any case, is already chosen to have the physical parameters which would allow for life, he wants to add this extra selection principle that life actually happened. And in 10 to the 100 of the, one part, only one part, and I don't know what the number he was invoking, but something like 10 to the minus 100 of the universes which would have the same physical characteristics as ours, life would occur. But since, in fact, in an infinite universe, when you have eternal inflation, everything happens an infinite number of times somewhere, life, therefore, will eventually occur somewhere, and that solves all of his problems, removes all constraints from him. Before he had to struggle, discover new mechanisms, which of course he discovered, but he couldn't discover any more. But this way he could just give up. And I must say the reaction of the biologists, and even more so the astrophysicists, was not kind. Well, I'm not going to go on with this. I just would like to summarize by showing you a poem that I discovered in The Nation called The Entropic Principle. And read this to you because it sort of summarizes in a beautiful way my feeling about the Entropic Principle. It says, so 3 drinks later, back in the office, I blast facts out my manifesto, which is simple. We should all relax. Apparently, no matter what we do, we already do our part. We balance the cosmological constant just by getting up in the morning and smacking around our wives. Isn't that amazing? And here's how it works. There could be an infinity of universes, starry bubbles, burning balls, solid balls of hard time. You name it, and they made it. Some are gelatinous, some are inside out, but there is one commonality. None are peopled. None have us. Only the composition of our universe allows for our existence. In fact, our presence is required, or the whole thing falls apart. So here's what I think. What if we all held our breath and stood sideways in a corner so we couldn't be found? Our universe would go wailing through the empty corridors of physics, knocking over furniture and pictures, searching for its vanished friends. Afterward, when we said, gotcha, and the universe wept with relief, we could all sit down for a nice cup of something comfy, have a heart-to-heart, and someone, somewhere, might wise up. So, to finish my sermon, since we're not sure what the final theory is, can't even formulate it, we're certainly not sure what the rules of the game are, we suspect that space and time are emergent. And in view of this, our understanding of the foundations are pretty shaky. And I think we cannot claim to know what the selection mechanism for the universe is. And just because we can't produce the solution is not evidence that it doesn't exist. So we shouldn't give up. What's the strategy? Well, the only strategy is to calculate, calculate, calculate. And you can do this if you believe in the Entropic Principle and you believe in the landscape. And we've heard some absolutely wonderful talks of exploring the landscape. It really doesn't matter, all of this preaching back and forth anyway. because most physicists will do what good theorists will do, what good theorists do, is to calculate and to observe. And that's good because, remarkably, I counted up the talks that couldn't have happened without one component. And that was 90% of the talks at this conference. Wouldn't have made any sense without one crucial component. And it wasn't string theory, by the way. It was supersymmetry. Except for two talks. One by Hermann Nicolai, who does string theory, does supersymmetry all the time, and there was one other talk, the Langlands, but no, that also too. There was one other talk. Everything else had supersymmetry. It really is remarkable how pervasive supersymmetry is in modern exploratory physics. And yet there's and certainly in string theory. In fact, I just checked to be sure with Julius today that it really is true that supersymmetry emerged from string theory. And Wes and Zumino were intrigued by a talk by Sekita where he discussed fermionic currents in two-dimensional world sheet string theories, led them to supersymmetry and higher dimensional field theories. That's right. That's right. Right. True. It's ironic. But Julius, is a pioneer always. But it is remarkable. And therefore, I think we are really lucky, as Michael Peskin explained. We have very strong, not only is supersymmetry such a pervasive part of our theoretical, our arsenal of tools and such an essential part of our attempts to go beyond what we know, it's also, and even though it has absolutely no experimental evidence, so this incredibly essential tool there is no evidence for, which is a really weird situation. But there are a lot of clues, as Michael stressed. The hierarchy problem, which points to the TV region. The existence of dark matter, which, if it's the lightest LSP, points to the TV region. And from my point of view, one of the original motivations for string theory and guts, coupling constant unification, the one quantitative hint we have, better than a % level of grand unification with gravity, which again requires supersymmetry and points to the TV region. You remember the requirement that you have supersymmetry to get this remarkable agreement after extrapolating the standard model over 14 orders of magnitude. This is an incredible thing. We have to take it seriously. In fact, we have to take all those three clues seriously. They all are natural predictions of supersymmetry, supersymmetric extensions of the standard model, which was not invented for that purpose, unlike many other things that come and go, and many have survived. It was invented to explain these weird two-dimensional quantum field theories. And then it was realized later it could answer these problems. So my opinion, as always, to take those original hints, especially of beautiful, elegant theories with so much power that gave answers to very difficult problems and were not invented for that purpose, and all point in the same direction very seriously. So that's why I continue to accept 50-50 bets for bottles of wine or whatever you want that supersymmetry will be discovered soon at the LHC. And so we are, as Michael said, very lucky. Because this tool, which it had been removed from our arsenal, we have to thank Julius, 90% of the talks at this conference could not have been given. we are going to probe in the next few years the regime where we have these very strong hints. So we have to hope that we will, since the tool is so essential for everything we do, and that these experiments will confirm our suspicions, our conviction, our intuition, and teach us a lot about what the correct strategy should be. So we have every reason, all of us, to wish the best for physics, and of course for Israel, and for Israeli physics, and especially for Eliezer and Shimon, who have done so much for all three. Thank you. Tom. They both correspond to Hilbert spaces with infinite dimensions. Indeed, all these different descriptions are very different looking, different degrees of freedom. No, but that's true of other dualities which are more traditional as well. Look, I think the situation, it really is almost scandalous that we know so little about how to. It's also, you remarked on the two cases where we have extremely powerful dualities and can formulate in those backgrounds string theory non-perturbatively, which are incredible. But we don't know how to do it in flat space. Flat space is sorry? Not really. Well, what is the dual description of the 10-dimensional scattering amplitude in flat space? I mean, of D0, of Lenny?
Now, there's one thing that occurs to me that the professor mentioned it has to do, I think you alluded to it to some extent, that all of the things that we know and understand really have to do with backgrounds which are asymptotically frozen, where an anti-de Sitter space is a space where the energy density rapidly goes to zero far away. Free particles can exist because there's nothing, there's no thermal heat out there and so forth. Flat space-time, matrix theory, all these things have to do with situations where far enough away everything is absolutely frozen cold. The universe isn't like that. The universe isn't like that. As far as we go out, we see stuff out there. It seems to me that a lot of the inability to get our hands on cosmology has to do with the fact that we somehow miss something very, very important about backgrounds which don't asymptotically go to something really frozen. Would you agree with that?
Well, sure. I mean, as you know, if we don't have stuff out there, then there are consistent cosmologies in string theory. There is empty space, which is a supersymmetric static solution. They're not our world. And so, I mean, this is one of the cases where we clearly don't know what the rules of the game are. Is the initial condition part of physics or not? If this is a is this a final theory? A theory, something missing from this theory? What is it? Is the initial condition, not to be described? We really don't know what the rules of the game is. This is not the kind of question. It's the kind of question people have asked forever, and have asked scientifically for a century. But we still don't know. And in the realm of all universes, there are closed universes. And I have no idea how to think about those in string theory or quantum gravity for that matter.
But even open ones that don't asymptotically become cold and empty.
Right.
We also really
Right.
don't have the first clue about how to think about it.
Yes, I agree. And as I said, there's a lot of focus on what it looks like at late times. But there's also early times where there definitely things would appear to be singular. And we avoid that. I still think that that's something string theorists shouldn't give up on. And even, for the younger people in the audience, even though your elders tried and failed, you should still think about it. I mean, that is the kind of problem string theory was one of its great potentials was to, and there was a flurry of attempts to understand. There still are wonderful ideas, actually. There's still, but it's. I don't have any answers. I just, what I really have is a very uneasy feeling that we're missing something big and that there's some reason, there can be reasons why our semi-classical intuition fails, which are not, and which are never going to be explainable in terms of the semi-classical intuition. It's like the failure of classical mechanics. You couldn't explain without understanding quantum mechanics what was wrong with those arguments. So just because you're in a regime where the usual criteria for semi-classical, field theory, all the tools we use, because we understand them, are valid, doesn't mean that it's correct.
You and I don't disagree about anything anymore, David.
Except the Entropic Principle. Okay.
So I would like, on behalf of the organizers, to thank all the speakers for wonderful talks. And I would like to thank one person who is not here, unfortunately, with us. That's Adam Schwimmer, who has, I think, Adam has done more than anyone else to make this meeting happen. And I also like to thank our secretary, Mrs. Ricky Cohen, and the wonderful technical staff, Simcha and his other colleagues. And we look forward to meeting you here again very soon. So thank you very much.